All right, are we good to go? Awesome. So, hello everyone. I'm Todd Charter. I'm the president and CTO of Cognia AI. I'm also a researcher at the University of Victoria. Today I'm going to be presenting about robotics and bridging the gap between research and real-world impact. I'm actually presenting on behalf of Dr. Homoyoun Najjaran, who runs the Advanced Control and Intelligent Systems Laboratory, which I'm affiliated with at UVic. So to get started, I'll just give you a bit of an introduction of who I am and my background. So I did my undergrad at University of British Columbia in Kelowna in electrical and computer engineering. And then I did my master's here at UVic, where I joined the lab working on intelligent manufacturing and robotics. I have experience in industrial automation, controls engineering, and mainly artificial intelligence. And I'm currently affiliated with two research groups on campus, the Advanced Control and Intelligent Systems Laboratory, ACES, as I mentioned, and the Graphics, Artificial Intelligence, Design, and Games Lab. And then as well, I have my company, Cognia AI, which I started with Dr. Najjaran about 2 years ago. And my main research interests: artificial intelligence, computer vision, cyber-physical systems, and robotics and automation. So the contents of the presentation today, I'm going to talk about the lab a little bit, go into our intelligent and adaptive robotics, our cyber-physical systems, and then I'll jump over to our aerial inspection and vision, where we're using drones, and then I'll finish it up with a little bit about my company and how we're commercializing what we do. So this is our lab, ACES Lab. It was founded in 2006 at UBC Okanagan. So we have over a quarter of a century, or almost a quarter of a century, in research in this area. So mainly our three areas of research are applied artificial intelligence, industrial automation, and cyber-physical systems. And I say applied artificial intelligence because we're not really computer scientists trying to develop all these new AI algorithms. We're mainly trying to adapt what's already there to make real-world impact. So we have four main teams in our lab. We have the mobile robotics and autonomous vehicles team, our industrial robotics team, computer vision and photogrammetry, and then the applied AI in industry, which is sort of a general umbrella term that encompasses things like business process analysis, machine scheduling, condition monitoring of machines, and those types of things. Everything we do in the lab is highly connected to industry, so we work with a lot of real-world projects and industry partners. On the bottom of the screen here, you can see a whole bunch of different industry partners that we've worked with in the past. And so everything we do, we do sort of software level, but eventually we have to show that our software works, so we eventually have to build prototypes and deploy it on real-world systems. So we do things from as small scale as micro-electromechanical devices all the way up to full-scale autonomous vehicles, aerial robotics, and everything in between. So it's a very diverse lab. We have a lot of different backgrounds: computer engineers, electrical engineers, mechanical engineers, computer scientists, and industrial engineers. So very diverse, but at the end of the day, everything that we're doing comes back to AI, and those topics sort of overlap in that sense. It's really great because we get a lot of different perspective, and allows us to brainstorm and come up with really unique and creative solutions. So I'll jump into our intelligent and adaptive robotics. This is something that a couple colleagues of mine at the lab have sort of come up with. This is our future of intelligent robotics in the center here, which shows how robots are going, or how we can teach robots using things like demonstrations and be able to break things down into different tasks or different skills in order to then be able to autonomously adapt in new scenarios. So rather than having to program robots to do things specifically every time, if you can break it down into individual tasks, they can go look up in their library of skills and tasks how to put those together, and then be able to adapt into new scenarios without having to specifically program it every time. Something that we do in the lab a lot is human-robot collaboration, and how can we work with these robots and communicate with the robots in a more effective and intuitive manner. And one medium that we use a lot is extended reality. So that's like augmented reality, virtual reality, mixed reality, those types of devices. So on the outside of this box, you can see different communication methods that we use extended reality for in order to communicate with the robot, teach the robot, program the robot, and all sorts of different aspects like that. So this is what extended reality looks like. It's a spectrum. We have on the one side the full reality, physical world, and then on the other side completely virtual, completely immersed, everything is digital. And then in between we have things like augmented reality, where you might use a device like a tablet or a cell phone, and you can see things overlaid on the physical world, or mixed reality glasses, where you can see things overlaid on the physical world, all the way to completely immersive virtual reality. So it's not just for gaming, it's also for interfacing with machines and equipment and tools and stuff like that. So I have a couple of demos that I'll share that kind of highlight these. So starting with this demo here. This is from a recent master's student in our lab. So he wanted to teach robots to use or to learn human skills in order to be better at certain tasks. So in this video, you'll see if you just program the robot to move the cup of coffee here, it's a very full cup and it spills all that because it doesn't know how to be delicate. So what the student did is he took a couple of XR devices and measured his own trajectories, moving the coffee very carefully. So these are just motion trackers that you would typically use in VR gaming. And he used it to create a data set of trajectories of his own personal movements, extracted some motion primitives, and then combined it with an AI algorithm called reinforcement learning in order to train the robot to be more delicate in certain tasks. It's a lot more complicated than that. I don't want to get into the nitty-gritty details there, but let's go back to the second one here is showing that same algorithm but in a different task. So here we have the goal is to stack some cubes, and these are all sort of toy examples, but they translate to real-world use cases. So this might be picking and placing parts in a production line. Here we see some Rubik's Cubes that we want to stack. So the robot has a camera on it. It identifies everything in the environment automatically. So those Rubik's Cubes were just mixed in there randomly. But using the vision, it was able to identify them, pick the biggest one first to put on the bottom. That green dot was the goal position there. And so now it's going to stack all of those Rubik's Cubes while avoiding that cup. The cup is just an obstacle. But the cool thing here is we're using that same sort of skill that it learned before, that human motion, that was trained from a human demonstration. So this is just one example of how that can apply for a different task. And then we have a couple other robotics examples here. So hopefully the internet wants to load today. Let me try opening it again, actually. Might have to skip that one. Let's go to our mobile robotics, see if that loads. Okay, well, it doesn't really want to load right now, but I can maybe give you a descriptive picture. So in this demonstration here, what we have is a robot wiping off marker on a whiteboard. And I mean, seems kind of trivial, just cleaning a whiteboard. But it really isn't that easy of a task, because you have to push on the whiteboard and give just enough force that you can wipe away stuff without pushing too hard or being too light. So using that same sort of concept of reinforcement learning with added parameters and added constraints, we trained a model that was able to not push too much force. Oh, here we go. Perfect. So let me put it on a little bit faster here so we can save time. So how this was done is they did some training using a force sensor, and they wanted to limit the amount of force that was put on the whiteboard. So they trained it with a force sensor, so it knows how much force it's putting. But when they deploy it in the real world, they take that force sensor off, and the algorithm is smart enough to be able to identify just from the robot's parameters how much force is too much. So here we can see now it's just on there to show us in the real world, but the actual algorithm doesn't use that force at all. This is just to show us that we're not exceeding our threshold. So how does that translate to an actual thing that you might need in the real world? For instance, on a car assembly line or a different manufacturing process, you might need to sand parts down, and that process you have to push to sand away the material, but you can't push too hard or it'll damage the robot, damage the part. So you need some sort of algorithm that's going to give that perception to the robot so it can complete the task. And I'll try this one just in case it loads. So we also have mobile robotics that we do in the lab. So autonomous driving, autonomous vehicles, that type of thing. Here we have this is called the Jackal. It's a little ground robot. And it has different AI algorithms built in that we've deployed on it. So this is just multi-object tracking. It identifies different objects in the room and gives them an ID. So it'll remember that this is chair A, not just a single chair. It's a specific chair. This is a specific person. But the goal of this is to do the autonomous path planning. So that yellow robot has a goal point, and it's automatically updating its path based on obstacles that it sees. So as I move those boxes, it now knows that, oh, I can go in between the boxes in order to get where I need to go. So that's some of our autonomous robots. Whoops, let's go back. So we're also, we started recently, I think a year and a half ago, a new research cluster on campus, which is called the Society Engaged AI and Robotics Research Cluster. And so what we're doing right now is we're building a whole room called our robot cell, where all the research that we do in this robot cell is for human-robot interaction. And so the Society Engaged AI and Robotics Research Cluster is not just us engineers that we deploy these AI algorithms on robots and stuff like that. It's actually a very multidisciplinary group. We have lawyers, social scientists, all sorts of different backgrounds coming together to talk about different challenges in AI, such as ethics and legal issues and stuff like that. So it's a really interesting group of diverse backgrounds that we talk about a lot of these very interesting problems that go beyond just the technology and consider more of those human factors in the society involved as well. So this just shows our robot cell here. I think this is a video showing one of the robots moving around. Kind of hard to see there, so maybe I'll skip this one. But this shows our simulated environment as well, very photorealistic. So we create this, we call it a digital twin, where our robots and our physical robots and our digital robots interact at the same time and update at the same time. So as you can change things in the digital twin and it'll update in the physical world, or as things change in the physical world, it'll update in the digital twin as well. So that allows us to do a lot of different rapid prototyping if we want to try things out in the digital world before deploying it in the physical world. Or if we want to do monitoring of our physical system, we can monitor it in the digital twin at the same time. And this software that we're using here is called IsaacSim. It's from NVIDIA, one of the best robotics softwares on the market right now for digital twinning. Let's see if I can play this. I don't think, yeah, here we go. This just kind of shows the room. So this actually matches our physical room completely to scale. So if you were to go into this digital world in virtual reality, it is exactly as if you're in the room that we've built. And you can manipulate those robots in virtual reality and have that happen directly in the physical room without even being in the room. So that allows us to do a lot more remote work, remote collaboration. And those are good for use cases where it might not be safe for the operators to be in there with the robots, or you might need to send the robot into an area that's not safe to be in, you can now monitor them remotely, but still feel like you're right next to them.
Question on that.
Sure.
How feasible is it to scale that up to, say, replicate a full production line?
Yeah,
Is that feasible?
totally feasible, and that's sort of the idea behind it. These might be small scale scenarios just to show the technology, but I have some other demos that I'll show that might interest you in that aspect as well. So our cyber-physical systems, I kind of alluded to that here with this digital twin. What is a cyber-physical system? Well, it is a connection of the cyber world and the physical world. So on the one hand, you have the physical devices such as your human-machine interfaces, your data collectors, your hardware, the physical devices, the physical machines. And then on the other side, you have all that software that powers it, the databases that store all the information, the control algorithms, the predictive analytics, and different interfaces like extended reality, all coming together to form this big cohesive system that we call a cyber-physical system. So we've actually developed a bit of a cyber-physical system in our lab, and this is the demo that I was talking about, which might be interesting. So this was just a little side project that I built a couple years ago to show all of the different robots interacting in tandem. So let me just, whoops, 1 second here. Let me just pause it for a second. So on the right here, you can see 2 video views of the physical lab, and this is the digital lab. I measured this all out and built this digital world to be completely identical to the physical lab. So you can see me in the real views there. I have a virtual reality headset on. I don't see anything real. I just see the simulation, which we call the digital twin. But I'm able to walk around the room. I'm not going to run into anything because I see the digital models that are completely synchronous with the real world. We built a little bit of a controller to be able to communicate with the robots. So here we have a little tiny drone. I put it in a bubble in the simulation just so you can see it better. And it's circled in red so you can see it in the physical world. But that little drone flies around, and I can walk around it without having to see it, but I see it in the digital world, and I know it's there. And then so I also built a couple little features just to show, for instance, here there's a laser pointer I built in to be able to tell the robots where to go. So when I click and point on the ground, a goal lights up there, and that yellow robot starts driving towards it. And then also the robots can communicate with each other. So that cyber part of that cyber-physical system allows them to share their information through the network. And so now we have the drone following that mobile robot so they can work together, share their information in order to get a better perspective of their surrounding and complete tasks collaboratively. So that's one aspect there. We also have a couple of robotic arms in the lab. So if I go forward a little bit here, you can see over on the left there's a couple robotic arms, and I'm just demonstrating a few simple pre-programmed movements just to show that they can be controlled from the digital world in the physical world. And everything is completely synchronous. It's, you know, the latency is so low that you wouldn't even notice a difference of being in the physical versus the digital world.
So just a quick thing then, that's not programmed behavior that you're seeing on the left-hand side. That's actually a reflection based on some sensors in the physical world that's being replicated in the digital twin? So
that is the physical world is, and the digital twin are updating their parameters based on the robot itself. Yeah, yeah. So that is, and then so we had another master's student that was working in the same sort of area. He was working more with mixed reality and things like that. And this is just a couple of his projects that he was working on as well. So he did virtual reality teleoperation. So again, controlling the robots using virtual reality. This is just a different interface of that same sort of digital environment. Telling the robots to move around. Let's see if I can skip forward a bit here. We saw a little bit of this in the last one. Just different ways of interacting with the robot and visualizing it. And you don't even need to be in the room. You could be somewhere, you could be at home even. And now this is mixed reality. So he's got glasses on that he can see the physical world, but there's overlays and things that he can interact with to control the robot just with hand gestures and voice commands. So he's completely hands-free, essentially, and he can just click and point and tell the robots what to do, and that communication goes through our cyber-physical system and updates on the robots themselves. Skip through a bit there. And so one of the other things that we work on a lot is 3D computer vision and 3D reconstruction. So these Rubik's Cubes that you see here, they're actual models created from taking a couple of different images and then creating a 3D model from those 2D images. So this is him interacting with it in a mixed reality, so those digital objects in the physical world. So that's a real table, but those are digital objects overlaid on the real table. And then he drops it on the ground there. So that 3D reconstruction, we can make objects like the Rubik's Cube, but we can also make whole environments. So this is a 3D reconstructed view of our lab. And you can see the CAD model of the robot overlaid in that 3D reconstruction that we made. There's a few little areas that look a little bit blurry. That's just areas that we didn't capture enough with the camera. And that whole 3D environment is created from just a select number of 2D images. So anywhere from 200 to 400 images is enough to create that sort of environment that we just saw there. So those are those demos. So now we want to take this and take those same concepts and talk about how we can use them with drones. So we built this autonomous data collection system for aerial photogrammetry and inspection. So it incorporates high precision data collection using sensor fusion software and multiple different sensors, RGB camera, time of flight camera, LiDAR, GPS, all of that information fused into one system. This is what the software kind of looks like. So we take in different sensor nodes, process all the data, and we can use it for our onboard processing to inform the drone itself, but also for offboard analysis after the fact. So we do a lot of inspection tasks, doing like infrastructure inspection. One of our bigger projects was for after disasters such as landslides, earthquakes, those types of things. We want to be able to go and inspect bridges and our other infrastructure to make sure that it's safe. But we can't go there because it might not be safe. So we want to be able to fly drones out there, collect all the data, build a 3D model, and inspect that model in order to come up with our analysis to determine different safety considerations and identify cracks and faults and whatever damages might have occurred. So what we're building is an intelligent aerial inspection system where the drone is smart enough to be able to identify what we want to inspect and collect that data autonomously. So how this looks is you would set a high-level target where you would say, okay, there's a bridge in this general area. I want you to fly over there and inspect that bridge. So the drone would begin to fly to that area that you pointed out, and it'll look for bridge, and it'll be able to identify, okay, here is the bridge. I've located the target. Next, it goes to the data collection method, which we use an intelligent method where as it's collecting different images or different data, whether it be LiDAR or whatever sensors it has, it processes that data and informs itself so that it knows what's the next best view to collect the most relevant data, rather than just doing a pre-planned path or a pre-planned flight where you might miss areas or you might over-collect on one part and not get enough of another part. It uses the data that it's collecting to inform itself, okay, I need more information about this side of the bridge, or I didn't fully capture that area over here, I have to go there next. So that's how the dynamic path optimization works. Question.
I assume that's a model that's complicated enough that it has to run off-board. So does that have a data link that does all the processing for it, or can that actually run?
So what we're doing right now is we do have a very high-performance computer on board an NVIDIA Jetson, which is good enough to run some basic models. We can't do the 3D reconstruction for our full analysis and inspection, but we can run that model to inform it of where to go in order to collect more relevant data. So that does happen on board. But yeah, the downstream tasks of inspecting and further creating the 3D models and that stuff, that's all off-board later processing. Yes?
Just to clarify that, you're saying that the dynamic path optimization model can run locally on the Jetson system, but the data collection analysis gets done.
Yes, yeah. So now we're working, this is sort of a new field of research in the lab where we're doing language embedding for our 3D reconstruction. And this is so that when we do inspection tasks, we can query our 3D model with natural language. For instance, say identify the support beams or identify cracks in a bridge, and just tell it natural language, and it'll be able to highlight those features in our 3D model so that we can quickly find them and look at them and analyze them how we need. So this is a bit of a complicated process, but we're using a reconstruction technique called 3D Gaussian splatting, in which we are creating a bunch of these Gaussians, millions and millions of points. It's like a point cloud, but they're actually ellipsoids with a whole bunch of different properties. They've got color using spherical harmonics, all sorts of different properties of the Gaussians themselves. But they create photorealistic 3D renderings. And you can move around to novel viewpoints that have never been seen before. So you have a 3D model just created from a bunch of 2D images. And then we're working to embed language features. So at the same time, when we create that 3D model that's photorealistic, we also do segmentation and language embedding of each segmented item, so that in those Gaussians now, it's not just their color and their location and their size and shape, but it also has underlying meaning, such as wooden bench or beam, bridge, like those language words that these big LLMs are using are now being embedded into the physical 3D model itself so that you can do downstream querying.
This is the complicated part, right?
This is complicated for sure. So this is what it looks like though. So this is what our 3D reconstructions look like. They're very photorealistic. This is a 3D model. You can move around in 3D space. Some areas here you can see are a bit blurry and black. Those are areas that we didn't take pictures of. But where we were looking at the target, very photorealistic, and you can zoom in on it and see and do your inspection. Part of the process, we do depth estimations. So not really used in our inspection per se, but used to create that 3D model. And then this is what the language features look like. So each different color in here, it's actually impossible to visualize those language features because they're very, very high dimensional. Typically, we're working with 512 dimensional language embeddings. But what we've done is we've condensed it down using PCA into RGB space, just so we can visualize, are they somewhat working? So here you see like this pink color would represent the wall. So that might be the word wall or different words that mean wall. The red over there might be concrete pathway. Green would be grass. And those language words are now just being visualized in the color space. But what that allows us to do is work with those and query that model. Yes?
I'm curious what models you run for this. So I'm familiar with vision models like Dino V3, for example, that does this really well. Not for 3D space, but for 2D space.
Exactly. So we do it in 2D and then project it into 3D the same way that we do our 3D reconstructions of the visual. We're doing that. So this is just to create a visual 3D model. And we use a bunch of 2D images to create that 3D model. Now, when we're doing the language feature fields, we use a bunch of 2D using like Clip or Dino to get those language features. And then we run the same process to create a 3D model, but now of language features, not of visual features. Yes?
So I am working on the embedded space, and it's not smooth manifold. So my question is, how do, with PCA you will lose information?
Yeah.
So they are not Euclidean space. So how do you deal with that?
So no. The PCA here is just for us to visualize. When we're querying our model, we're using the full feature space, just so that we can see, is it working? Does it look like it's actually putting language features in the right spots? That's what we use PCA for. But when we're actually working with it, we're using the full feature space.
Okay, and and also it's not continuous. You can the data are high-dimensional data, right?
Yes.
You cannot apply continuous derivative function to understand the curvature of those stuff in order to go deeper. So how do you deal with that?
So we're not actually, we're not doing anything there. What we're doing is we're taking those embeddings and we're just putting them as parameters in our 3D Gaussians. And then when we query, we're just feature matching to pick up those, which Gaussians match our query. So I think this video might not work, but let's see if I can give it a go. I don't think so. So unfortunately, I had a couple of demonstrations here that kind of showed what our 3D models look like, but they don't want to work for you guys today, unfortunately. But this is one of our 3D models. This is a gazebo over in Crofton. We actually had a big 3-year project that was a multi-group project. We had NRC from Montreal, University of Ottawa, Toronto Metropolitan University, and a bunch of different collaborators coming together on this 3-year drone project, where some teams were working on just the drone obstacle avoidance, and then our team at UVic, we were working on the 3D reconstruction and inspection. And so back in September, we had our final demonstration where we went to Crofton, we flew around the bay there, collected some data of different structures and created 3D models. So this is one of them. And then, unfortunately, I can't show you the video, but this is another one of the language embedding. I promise they work. And I think that, yeah, so this is the same sort of picture that you would have saw there. So in this case, this light green color might represent the roof of the gazebo, whereas this pinkish color represents the railings or the wall. So now I'll talk a little bit about Cognia AI, which is the company that I founded about 2 years ago with Professor Najjaran. So we're built on same sort of research coming out of the Advanced Control and Intelligent Systems Laboratory. So we have over 25 years of experience and background in this AI or intelligent algorithms space. So we specialize in AI-driven solutions to enhance automation, decision-making, and inspection processes. We've been collaborating with global partners, leading research organizations, and industry partners. And we're even trusted by other software companies where our uncertainty quantification has been helping them to better understand their own AI models. And we do that in ongoing projects. Our main areas of expertise are 3D perception and computer vision, uncertainty management and uncertainty quantification and risk management, intelligent systems and decision support, and industrial automation and adaptive robotics. We have a few services that we provide. These are our 5 main services: process optimization, uncertainty quantification, anomaly detection, 3D mapping and inspection, and condition monitoring. And yeah, that's everything. Thank you guys for listening. Feel free to reach out to me with any questions.